Hey everyone, Vivek here. In the last video, we have discussed position vector with some examples. And in this video, we will build up some basic understanding of unit vector and velocity vector. Any vector that has a magnitude of 1 is called as unit vector. In a two-dimensional space having the origin O, take a point P, which is at a unit distance from the origin. So vector OP will be a unit vector. If we draw a circle having a center at O and of a unit radius, and draw a vector joining a point O to any point on the circumference, then this is also a unit vector. In this way, we get an infinite number of unit vectors having a different direction. Vector OP makes an angle alpha with a positive x-axis. We can easily calculate OM and MP. In a right angle triangle OPM, cos alpha equals OM by OP. So OM equals OP cos alpha. Similarly, MP equals OP sin alpha. Vector OP is a sum of vector OM and vector MP. Here the vector OP has a unit length. So vector OP equals to cos alpha x cap plus sin alpha y cap. As we vary alpha, we will get a unit vector in a different direction. Now let's find out the unit vector in direction of vector OB. It cuts the circle at point A. So we have got unit vector OA. This vector makes an angle theta with the x-axis. We can easily find out this vector OA, that is equals to cos theta x cap plus sin theta y cap. If we don't know the angle theta, there is another way to calculate this vector OA. Let yourself pause and ponder. How many vector OA can we fit in a vector OB? The answer is magnitude of vector OB. Vector OB can be written as a product of its magnitude with a unit vector. It's our tradition to put cap on OB to represent it as a unit vector. Here OB cap is a unit vector of vector OB. Unit vector is important to represent the direction. Once we have a unit vector, we change the magnitude by a factor of whatever we want, and we can make any length vector in a specific direction. If we keep the magnitude constant and change the orientation of unit vector, we can make the same length vector in any direction. Now we have a basic understanding of what the unit vector is and how to calculate it. Now it's time to learn the velocity vector. But to understand it, we need to have some background on what the derivative and slope is. So let's have a quick look at the slope and how to calculate it. Suppose we have a function f of x equals to x square. If you don't know how to plot it, let's figure it out together. Put different value of x in function, you will get corresponding value of function y. Mark the point on the two-dimensional plane, join the points, and at least you will get some idea about how the plot will look like. If you take as many as points on the plane, your plot will look smoother. Derivative at any point is the slope of tangent at that point. We want to calculate derivative at point P. For that, we draw a tangent at this point, and this tangent makes an angle theta with a positive x-axis. Derivative at point P can be written as a tan theta. For now, just stick to it. Later in another video, we will discuss derivative in detail. Here you can see how the slope of tangent is changing at a different point. So does the derivative. If a particle is moving along some curve y equals f of x, then its velocity will be in direction of tangent to that point. Length of velocity vector represents its speed at that moment, and direction of velocity vector tells us the direction in which the particle will go. A particle or body always moves in a direction of tangent. Here the velocity vector of a particle is changing with time. When the particle is at point P, its speed is v, and we want to calculate the velocity vector at this moment. Velocity can be written as a product of its magnitude, that is speed, and the unit vector in direction of velocity. We know the speed. If we just know the angle theta, that the tangent at this point makes with the positive x-axis, we know the unit vector. And finally velocity vector, that is v cos theta x cap plus v sin theta y cap. Here you got the two components of velocity, v cos theta and v sin theta. If we put the light above the curve and let's assume that the rays are coming parallel to the y-axis, then a shadow of particle will form on the x-axis. Can you guess that with what speed the shadow of particle is moving along the x-axis when the particle is at point P? That is v cos theta. Can you again guess with what speed the shadow of particle is moving along y-axis at that moment? That is v sin theta. You can see how the x and y component of velocity are related with each other. When you throw a ball on the surface, it goes up to a certain distance and then it stops. If you draw a velocity vector at any moment, then the length of the velocity vector tells you about its speed at that moment, and direction tells you about that in the next moment in which direction the ball will go. See how the velocity vector is changing. Even though the direction of velocity is constant, speed is continuously decreasing because of the rough surface. Here, friction is opposing the motion of ball. This car is going from one hill station to other hill station with a constant speed. Even though the speed is constant, the direction of velocity is changing throughout the journey. The direction of car velocity at any point is tangent to the path at that point. If you know the velocity vector at every moment, you can exactly trace the path on which the car is moving. You will get the exact equation of path. Now it's time to make an apple fall. When an apple is just about to fall, its speed is 0. But as it falls down, the speed of apple increases with time because of the gravity. We can see how the velocity vector is changing with time. When it is here, the length of velocity vector is less, and when it is here, the length is more. Have you noticed if you make a hole at the bottom of the tank full of water, water starts to fall, and a little water vortex is generated in a tank. Velocity near the center of vortex is more. Let's see the water in the tank from the upside. If we slow down the time and look carefully, we will see particles are going in a spiral path. We can see now how the length and direction of velocity vector attached with particles are changing. As the particles are approaching the center, the length of velocity vector increases. So if either of magnitude or direction of velocity is changing, there must be some force acting on that particle, a body. This is Newton's first law of inertia. Thanks for watching.